Hello and welcome back to the channel. In our previous video, we built a basic 3-node Ceph storage cluster. Today, we are taking the next step, integrating that Ceph cluster with OpenStack. We'll walk through configuring OpenStack to use Ceph as the backend for images, volumes, and backups. Along the way, we'll explore the key services that power the OpenStack storage layer, and we'll see how Ceph features like snapshots, copy on write, and cloning can dramatically speed up instance provisioning. Finally, I will run a few demos to show these features in action. My name is Philip, let's get started. Before we dive into Ceph, let's quickly look at some basics like how storage is handled in OpenStack. At a high level, there are two main services to remember: Glance and Cinder. Glance is the image service. It stores and manages operating system images the instances boot from. By default, it uses a simple file backend, but it can also leverage scalable storage systems like Swift or Ceph. Cinder, on the other hand, provides block storage in the form of volumes. These volumes are persistent, meaning your data survives even if the instance using it is deleted. On top of that, Cinder supports features like snapshots, which capture point-in-time copy of data, and cloning, which lets you quickly spin up identical copies of volumes. Together, Glance and Cinder form the backbone of OpenStack storage layer. Images for provisioning, volumes for persistence, and advanced features like snapshots and clones for flexibility. Together, Glance and Cinder give us the essential building blocks for storage in OpenStack. But storage doesn't exist in isolation. It's closely tied to compute. Every time we launch a virtual machine, Nova, the compute service, has to work with Glance to fetch the right image and create a disk for that instance. Nova, the compute service, is responsible for provisioning and managing virtual machines, also known as instances. Nova creates, starts, stops, and terminates VMs. It also places instances on the most suitable compute nodes based on resource requirements. Nova talks to the hypervisor on the host via libvirt API, so it doesn't need to know the low-level details of each hypervisor. Let's now switch gears and look at how Nova interacts with Glance when provisioning a new VM. When you create a VM, by default, OpenStack will perform boot from image operation. That uses an ephemeral disk. Ephemeral disk is a temporary storage. It's automatically created when the instance is launched and is deleted when the instance is terminated. To create an instance, we need an OS image. Let's upload a new image named Zeros into the OpenStack Glance image service. We'll specify the format of disk as QEMU copy on write, set the container as bare, and make it visible to all the tenants. In the Cola Ansible setup, all OpenStack services run as Docker containers. That means Glance itself doesn't store data inside the container. Instead, it relies on Docker volume for persistent storage. If we look closely, var lib glance inside the container is mapped to var lib docker volumes glance data on the host. Let's list that folder. There's our Zeros image. It's stored as a regular file in QEMU copy on write format. So to sum up, by default, Glance uses file backend. This means that image files are saved directly on the server local disk. Mind that the metadata is stored in the database and the image's actual data is stored as a QEMU copy on write file. With our image in place, let's go ahead and launch an instance using it. I will set the flavor to M1 Tiny and the image as Zeros. Flavor specifies the hardware configuration for the server, like number of CPUs, amount of RAM, and size of boot disk. Based on the selected flavor, Nova knows how large a root disk to provision for the instance. The image parameter specifies the operating system image that the server will be booted from. We'll point it to the image we've just uploaded. Now let's break down what's happening behind the scenes. The request goes to Nova API container. The Nova API service validates the request and sends a command to the Nova scheduler, which decides which compute node should host the new instance. Since we have all-in-one deployment, it will schedule it on the local host. Then the Nova Compute service, through the libvirt driver, copies the image from Glance to its local cache. This image will then act as a read-only backing file for new instances, allowing for faster boot times. Nova will then create an ephemeral disk. It's a sparse copy-on-write image file backed by this cache base image. That's an overlay on top of base image. It initially takes up almost no disk space and only grows as changes are written to it. You may ask, why not clone the image directly from Glance into the ephemeral disk, but use a cache-based image? In this example, the Glance image backend is a file on local disk, but often the Glance backend is remote, like OpenStack Swift object storage or Ceph block device. So imagine, every time you launch a new instance, you'd be pulling the entire file across the network from Glance storage backend. This would create a massive network bottleneck. With local caching and copy-on-write feature, you only download the image once and then use it as a base image for multiple VMs. Second question you may have, why to use ephemeral disks at all? Ephemeral disk is on local storage of the compute node. It offers very low latency I/O performance. This is beneficial for applications that require high disk read-write speeds. However, when the compute instance is deleted or the compute host crashes, the ephemeral disk is lost. As you can see, the disk is no longer there. Only the base image is left. So, when you create a new virtual machine, Nova won't contact Glance for new image. It will use a pre-downloaded cached image located in the base directory. Nova is the compute service in OpenStack. It provisions and manages virtual machines by working with the hypervisor through libvirt without worrying about hypervisor-specific details. Instances are usually booted from an image provided by Glance, the image service. Glance stores OS images in different backends like local file system, S3, Swift or Ceph, while keeping metadata in database. Nova caches these images locally. By default, Nova creates ephemeral disks, fast, low latency local storage that disappears when the instance is deleted. This makes them great for performance, but unsuitable for persistent workloads. We've seen how instances boot from images and rely on ephemeral disks, which vanish when the VM is terminated. But what if we need data to survive instance restarts, migrations, or failures? This is where Cinder, the block storage service, comes in. Unlike ephemeral storage, Cinder volumes are persistent, independent of compute nodes, and can be attached or detached from instance as needed. Using Cinder for boot volumes or data volumes gives you durability, flexibility, and advanced features like snapshots, backups, and integration with enterprise storage backends. Let's see how Cinder works, why it's a step up from ephemeral disks, and how to use it for persistent storage in OpenStack. In our first demo, let's create an empty volume that's 10 GB in size. Now let's provision an instance with an ephemeral disk. As you may guess, we'll now attach this newly created volume to the instance to provide additional storage space. To do that, we'll just use OpenStack server add volume command. Mind that delete on termination is set to false, so the volume will not be automatically deleted when the instance it's attached to is terminated or deleted. Let's log into our server. To do that, I will allocate a floating IP from the external network. Then let's associate that IP with our VM. Finally, let me log into the VM using that floating IP. Our server has two disks, dev VDA, that's the ephemeral disk with the operating system, and dev VDB is our volume. As the volume is a blank block device, before we can use it, we need to create a file system first. Let me do that. Let's now create a new directory and mount our disk there. Let's create a test file, put some text and save it. Now let me log out from the instance and delete it. Although there is no server present, the volume itself was not destroyed when the instance was deleted. The instance is just a virtual machine that's attached to the volume. Deleting the instance simply breaks this link and stops the VM from running, but the data on the volume remains completely untouched. To prove that, let me create another VM. Now let's attach the existing disk with all its data to this brand new virtual machine, allowing access to our files again. Let me also associate the same external IP to the instance. Now let me remove the SSH host key for that IP as it changed and log into the instance. Now let me mount the volume and voila, despite it's a different VM, our files are still there. In our simple cluster, the Cinder volume is backed by Linux LVM. I've created a Cinder volumes LVM volume group. Within that group, we have a so-called tin pool. It's a special type of logical volume that acts as a container for other logical volumes. Then we have a tin volume. It's a logical volume that doesn't pre-allocate its full size. Instead, it draws storage from the Cinder volumes pool as data is written to it. At the moment, it only occupies a few percent of its 10 GB virtual size. So, our Cinder volume is backed by an LVM tin volume. Just so we are on the same page. In OpenStack CLI, you are working with Cinder volumes. However, on the LVM storage host, you are working with the LVM tin volumes that are backing the Cinder volumes. Instead of creating an empty volume, we can also create one directly from a disk image. This essentially clones the image into a brand new persistent volume. Let's try that now. I will use the Ceros image as the source, set the volume size to 10 GB and call it boot volume. Great, we've just created a new volume that's an exact copy of the Ceros image. This volume can now serve as a boot disk for a new instance. Instead of specifying an image when we launch the instance, we'll point directly to the boot volume. By using --volume, we are telling OpenStack to boot this server from an existing Cinder volume called boot volume. This approach is often referred as boot from volume. Notice here that the image field shows NA. That's because the server wasn't created with an ephemeral root disk. Instead, it's running entirely from the Cinder volume we just created. This is an important best practice. Booting from volumes ensures data persistence. Even if you delete the server, the data stored on the Cinder volume remains intact. Sometimes you'll want to create a new volume based on a snapshot of an existing one. This is super handy for testing, cloning environments, or rolling back to a known good state. Let's walk through the process. First, let's delete our demo server so its volume is not in use. Now let's create a snapshot of our boot volume and name it snap1. Snapshot is a read-only point-in-time copy of data. It captures the state of a volume at an exact moment it's taken. Now let's create a new volume from that snapshot. I will set the size to 10 GB and name it boot volume clone. And there it is, our new volume, created directly from the snapshot. This volume can now be attached to a server or even used as a boot disk, just like any other Cinder volume. Using volumes unlock possibilities that local storage simply can't provide. The first big benefit is data persistence. If your instance crashes, gets deleted, or you need to reprovision it, your data stays safe on that volume. That's absolutely critical for databases, application data, user files, logs, basically anything that needs to survive beyond the life of a single VM. And because volumes can come from a storage cluster, you also gain scalability, redundancy, and better performance compared to local disks. The second major advantage is decoupling compute from storage. If an instance becomes unhealthy, you can speed up a new one and simply reattach the existing volume, minimizing downtime. This also makes it easy to change instances types without losing data. On top of that, volumes are portable. You can detach and reattach between instances for maintenance, scaling, or even manual disaster recovery. Another huge plus is flexibility. Volumes can often be extended on the fly without downtime, and with snapshots you can capture point-in-time copies of your data, perfect for testing, cloning, or restoring a previous state. Volumes bring persistence, portability, scalability, and resilience, making them a cornerstone of reliable cloud workloads. So far, we've been using local storage to host ephemeral disks, glance images, and cinder volumes. That works fine for testing or small environments, but for a real production OpenStack cluster, you need something far more scalable and resilient. That's where Ceph comes in. Ceph is a distributed storage system that provides object, block, and file storage all in one unified platform. It scales out across multiple servers, giving you redundancy, high availability, and strong performance. In OpenStack, Ceph integrates directly with the core services. Nova can use Ceph to store ephemeral disks, Glance can store images in Ceph RBD, Cinder can use Ceph as its backend for volumes and snapshots, cinder-backup can use Ceph for backups. The benefit here is huge. Instead of relying on the local disks of your controller or compute nodes, all these services share the same reliable distributed Ceph storage cluster. That means better fault tolerance, easier scaling, and no single point of failure. In the last video, we built a working Ceph cluster. Now it's time to connect the dots. Reconfigure our OpenStack deployment to use that Ceph cluster as the storage backend. For this demo, we'll use Ceph block devices across all services. The plan is straightforward. Configure Cinder and cinder-backup to store volumes and backups on Ceph RBD, reconfigure Glance so images are saved directly to Ceph, and update Nova so ephemeral disks also run on Ceph. By the end of this video, we'll have a fully integrated OpenStack setup where every major service uses Ceph for storage. And because everything runs on Ceph RBD, we'll unlock some powerful optimizations. Let's dive in. Each OpenStack service uses its own Ceph pool. So let's start by creating them. I'll go to our Ceph cluster and enter its shell. Now let's create 4 pools. One for Cinder volumes, one for Glance images, one for Nova ephemeral disks, and one for Cinder backups. These names match what OpenStack expects by default. You can use custom names, but then you'd need to update the Cola global configuration file accordingly. For simplicity, I will stick to the defaults. Also note, multiple services can share the same pool if needed. Next, we need to tell Ceph what kind of data each pool will store. Then let's initialize the pools for use with Rados block device, RBD. At this point, our Ceph pools are ready, but for OpenStack services to actually use them, we need credentials. Each service can have its own permissions, but to keep things simple, we'll create just 2 users. First, we'll set up a user for Glance service, so it can access the images pool. We need to grant this user access to Ceph monitors with RBD profile that provides the minimum necessary permissions for an RBD client. We also need to grant permissions to storage daemons OSDs. Profile RBD grants read-write permissions to the images pool. With these credentials, the Glance service can connect to Ceph, access the images pool, and store and retrieve images. The other user will be shared among Cinder, cinder-backup, and Nova services. We'll grant it access to all the pools, that is, volumes, backups, VMs, and images. Why? Nova will use this user to create ephemeral disks in the VMs pool. But it also needs to fetch operating system images from the images pool when booting new instances. cinder-backup needs to access both the volumes and backups pool in order to create and restore backups. And Cinder itself, of course, needs access to the volumes pool for provisioning block storage, but also images pool to perform copy-on-write clones from Glance images. By giving this single user access to all the pools, we simplify the setup while still ensuring each service can do its job properly. Mind that, for production builds, you should create individual Ceph users for each service and grant them only the minimum permissions they require. Our Ceph configuration is ready. The next step is to reconfigure the OpenStack cluster to use Ceph as its backend. We'll start by editing the Ansible global configuration file. I already have these values set, so let's review them. Here we enable Cinder volume. It's not enabled by default. Here we set Cinder to use an external Ceph cluster as its backend. Now let's move to cinder-backup. That's a service responsible for backup and restoration of Cinder volumes. Here we enable it. Here we set cinder-backup to use Ceph as its backend. By default, cinder-backup will use the cinder-backup user to authenticate. Here we tell it to use the shared Cinder user. Our next service is Glance, the image service. Here we tell OpenStack to use Ceph as its backend. Finally, Nova, the compute service. Here we configure it to use Ceph as the backend for ephemeral disks. By default, it uses Nova user to authenticate to Ceph cluster. Here we override that and set the user to Cinder. The global configuration file also allows you to override default Ceph RBD pool names and authentication users for each service. Before running Ansible deploy or Ansible reconfigure, depending on whether you are deploying a new cluster or updating an existing one, there's one more step. As we saw in the previous video, a client connecting to a Ceph cluster needs two files: ceph.conf that holds monitor addresses and keyring file that holds user credentials. Since every service runs in a Docker container, we need to inject these files into the appropriate containers. The host directory, etc config, serves as the base configuration path. We need to create subdirectories for each service group, and files placed inside those directories are then mounted into their respective containers during deployment. For our setup, we need the ceph.conf and keyring files in Glance, Nova, Cinder volume, and cinder-backup containers. Let's place the ceph.conf file in each directory. To do that, I will list the contents of that file on the Ceph cluster. Then let me paste it inside the Glance directory. I will also copy the file to Nova and Cinder directories, as each container requires its own Ceph configuration file. The second file needed to connect is the keyring containing credentials. Let's first obtain the credentials for Glance user, then let's paste it in the keyring file under the Glance folder. Let's now get the credentials for the Cinder user. I will then paste those in the keyring file under the Cinder directories. Let's also copy the keyring to the Nova folder. For snapshots to work, we need to set one more property. Oh boy, we've spent quite a while preparing our config files. This is how the final result looks like. Now, during OpenStack deployment, those files will be mounted inside the respective containers, so each OpenStack service can connect to the Ceph backends. If you are building a new cluster, just run Ansible deploy. I'm modifying an existing cluster, so I will go with reconfigure option. Once this is complete, let's verify that storage services are running. Just as an example, if we go inside Nova compute container, we can see the Ceph configuration file as well as the keyring with credentials. Okay, our OpenStack with Ceph backends are ready. Let's now see it in action. First, let's get a small OS image. Cirrus is perfect. By default, it's in QEMU copy on write format. For Ceph snapshots and cloning to work, let's convert that image to RAW format. Let's now upload the image to Glance and verify the image creation in OpenStack. Next, if we list the image pool in Ceph, we'll see a new RBD image uploaded. Mind that the RBD image name matches Glance ID. Apart from Ceph image, Glance also creates a protected snapshot that is read-only point-in-time view of our data. Why? If you recall from our last video, that's the first step to perform cloning. As we have our Glance image ready, let's create a Cinder volume from that image. Let's verify that Cinder volume has been created. Okay, it's there. Next, let's take a look at the Ceph cluster. There's a new RBD image. Its name matches the Cinder volume ID. You will say, so what? We've not seen anything new. Wait for it. If we display information about this RBD, we see it has a parent. This Cinder volume is a child of the Glance image snapshot. If we look at the parent snapshot, we see it has a child. This confirms it's a copy-on-write clone. This design offers a huge optimization as it's a thin volume, very fast to create and uses no space initially. That's exactly how OpenStack with Ceph can spin up new VM volumes super fast. They are basically instant clones that don't take up any space until you actually use them. And that's a big reason why this setup can power really large cloud systems without slowing down. Let's now boot our VM using the volume as its root disk. Then I will check if it's running. Here we can see the VM was booted from a Cinder volume. If we now go to Ceph shell and look at the status of that boot volume, we'll see a watcher. What is that? VM boots and QEMU open its RBD-backed disk. QEMU acquires an exclusive lock on the image. That ensures no two clients write at once. At the same time, it registers a watcher. The watcher ensures QEMU is notified if the image is resized, snapshots are created or removed, the image is flattened or cloned. We also see which host is actually holding the watcher. Lastly, let's boot a second VM directly from an image. If we look at the server list, we'll see the image name the compute service used to provision the ephemeral disk. If we list the VMs pool in Ceph, we'll see a new Ceph RBD image. That's the VM's ephemeral disk. After inspecting that RBD, we see it's still a copy-on-write clone of the Cirrus OS image snapshot. If we look at the snapshot, now it has two children. One is the boot volume and one is the ephemeral disk. This demonstrates the power of using Ceph RBD as backend for images, volumes, and ephemeral disks. With features like snapshots, clones, and copy-on-write happening seamlessly in the background, performance is significantly enhanced while also saving storage space. Lastly, let's initiate a backup process for our boot volume. I will add the force flag as the volume is in use. Next, let's list available backups. We see the incremental flag set to false. This means it's a full copy. cinder-backup stores full backups as a new RBD image in the backups pool. If we inspect that image, we'll see it's a full RBD image, a copy of the entire volume data. Moreover, cinder-backup also creates a snapshot of this new backup image. This snapshot serves as the base or parent for the next incremental backup. Now, if we create another backup of the same volume, but this time with the incremental option, we'll see another backup, this time an incremental one. However, behind the scenes, Cinder creates a new snapshot of the same RBD image in the backups pool. If we list the backups pool, we don't see a new image, but instead we'll find another snapshot. Ceph uses diff command to compare the new snapshot to the previous snapshot. It exports only the changed blocks from the source volume and imports them to the new snapshot of the backup image. The new snapshot effectively contains a pointer to the previous snapshot, creating a snapshot chain. The new snapshot only holds the changes, while the previous snapshot holds the data from its point in time. And that wraps our deep dive into OpenStack storage with Ceph. We started with the basics: images, volumes, ephemeral disks, and snapshots, and saw how Nova, Glance, and Cinder work together. Then we moved on to integrating Ceph as a backend, giving us distributed, resilient storage across all services. Along the way, we tested key features like snapshots, copy-on-write cloning, and backups, and saw how they make instance provisioning faster, more efficient, and more reliable. Ceph doesn't just add persistence. It brings scalability, fault tolerance, and performance that local storage cannot match. That's why it's the go-to solution for production-grade OpenStack deployments. Thanks for watching, and I'll see you in the next one.